So, welcome to the first lecture in Introduction Lattice Boltzmann method in winter term 2022-23. This lecture is being recorded, so please don't say anything that we later have to edit out. Yeah, but otherwise you're very welcome to participate here. I closed the windows because it's a little bit loud outside, so if you fear that you get infected, then please wear your mask. Okay, introduction to Lattice Boltzmann method. Very briefly in the beginning, what all of this is about. We are looking at a crazy method that uses particles that are moving on what we call a lattice. So this is a regular arrangement of points in space. So particles are moving around on this, and we make this lattice very large, put this into some geometry, like actually this is the building that you see here is the building where you're actually currently in. And then we do this simulation. We solve the so-called Lattice Boltzmann equation, which is this thing here, which unfortunately I don't have, see here, which is this thing here, and which is what we learn in this lecture, in this lecture series. And this then gives us the movement of the air, actually is solving the Navier-Stokes equation. Okay, so this is, so now Navier-Stokes equation is down here, and then you get a crazy flow field around these buildings. Oh, I have to stay close to the mic, otherwise I'm not recorded. Okay, so this is more or less the big picture and the graphical abstract of today. So this is today we are talking about the Boltzmann equation, which is different from the Lattice Boltzmann equation, but we'll have to understand the Boltzmann equation first to go to the Lattice Boltzmann equation. So the content of today's lecture is three different ways to understand the world. Yeah, then we look at one of them, namely the one in the middle here, the Boltzmann equation. We look how this works with the collision integral, with conserved quantities, and in the end we will derive the so-called ether theorem, yeah? H or ether theorem. Okay, so the ether theorem is the thing that tells us in which direction time progresses, yeah? Because time could go forward or backward. And the ether theorem tells us that what is forward in time and what is backward in time. Okay, so this is something that we learned today. And let's jump into the subject. So, okay, the three worlds, now I have to change my pen. So there are three ways, and maybe there are more, but they are the ones that we are using, three ways to understand the world. To see, to see the world. So, and the first one is to say there are atoms, so there's an atomistic view, or there are molecules maybe, which is an assembly of atoms, of course. And this is just using Newton's laws for, say, a molecule I. There's a molecule that we call I. So this is I is a number, and this follows Newton's law. So this molecule I has a mass mi, and it has an acceleration ai, And this is nothing else than the sum over Ij Fij, where J is the number of a different molecule. Like we have many of them, say this here will be our particle 1, and this here will be our particle 2, and 3, and 4. And then there is this force F1, 2, going this way. There's a force 2, 3, 4. Then there is a force F3, 1, that's going this way, and an F3, 4 going this way, an F4, 2 going this way, and then there are others in between, F1, 4. So between all the particles we have forces, and they all go in 2 directions, as you should know from axial equals action equals reaction. Yeah? So the one force that acts on particle 1 from particle 2 is the inverse of the other one. So this atomic, the important thing with this atomic picture is that we are looking at distinct particles. So what do I mean with distinct? Distinct means that every particle has a name. So there is a specific particle. So we start with a specific particle and we observe this particle for hundreds of years and we say, okay, one particle came through the window and we wait until this particular particle leaves through the door. Yeah? It's not like there are trillions of nitrogen molecules entering, and some entering there, and we don't know which one. Here we know each one. So the particles are distinct. And they exchange, they're distinct and they exchange energy and momentum by the Newton's laws. And they are doing this by binary forces. So interaction always between 2 particles, not between several at the same time. So this is one way how you could imagine the world. So another way to imagine the world is the continuous picture. And this is usually described by the Navier-Stokes equation. So I assume that what I just told you is absolutely nothing new to you. Yeah? So you know Newton's laws, you know there are molecules and they interact with each other and they are binary forces and nothing else in principle. And I would also expect that you have heard about the Navier-Stokes equation, maybe to a lesser extent, but you still should have heard about this. Somebody never heard about the Navier-Stokes equation? Okay, nobody is reacting. So the Navier-Stokes equation is an equation of a velocity field, the time change in a velocity u, that comes with something that we call an advection term. So this thing here is advection. And the entire thing, so what is, how do you call this entire thing? Somebody? Give me some interaction. No? The material derivative. You heard the material, you heard about the material derivative. Okay. So this is the material derivative. So it's the change in time in a frame of reference moving with the stuff. By the way, we are not supposed to drink in this room. There's a sign in the entrance. So just okay. So this is what we usually put on the left-hand side, the material derivative, and on the right-hand side we have the potential term. So this is usually given by the pressure difference. And there is a diffusion term. Diffusion term that in the simple case of a Newtonian fluid looks like this. Could be more involved. So this is the diffusion. And then there is something that we actually derive the name of all of this. This is the time derivative of the density, which is rho the derivative of u, and this is a continuity equation. So this is actually the incompressible continuity equation. Yeah. So and this is the thing that gives the name to this view of the world. So if you like to see the world like this, then you are very much okay, so you are in principle in good company, but you also think a little bit 19th century way of thinking. So you have flowing matter is a continuous field now, and also this field is obeying Newton's laws and conservation, and this leads to conservation of mass, momentum. So one thing that is often forgotten that this conserves is angular momentum. So this also conserves angular momentum. Not beautiful. And it also conserves energy potentially. So if we write down the incompressible Navier-Stokes equation, we have forgotten about temperature, and therefore this Navier-Stokes equation does not conserve energy. Yeah. So this is why I put this into brackets. Yeah. But in principle, we could also write an energy equation on top of this, and then we also would conserve energy. So why did I say that this is 19th century like? Since when do people believe in atoms? Or who was the first to believe in atoms? John Dalton? Oh, when was John Dalton? I mean, there was somebody before John Dalton believing in atoms, certainly. So in Greece, 3,000 years ago, they believed in atoms. So this was of course known, yeah. But many things that were believed in 3,000 years ago, of course, were wrong and were later not believed anymore. So the old Greeks, they believed in atoms. Yeah, fire, earth, water, somehow elements, atoms. So when did people, when did we, like in the modern age, started to believe in atoms? Where's this idea coming from? Okay, I tell you, in the middle of the 19th century, people had this kind of theory, but that there was actually a proof that real physicists would start to believe that this makes sense was only in the beginning of the 20th century. So the Navier-Stokes equation is much older than the belief in atoms. Yeah? So this is why we don't need atoms here. We can describe the world like this, and this is a continuum. Yeah? So the atomistic view of the world, we need for understanding the Boltzmann equation, we need an atomistic view of the world, but the atomistic view of the world is accepted only. Actually, there was a paper by Albert Einstein in one of these papers by Albert Einstein in 1905 that actually proved that the viscosity term, this is this here, is incompatible with the assumption of a continuum. Yeah, and through this he could actually prove the size of an atom. Yeah, so you can take the viscosity, and from the viscosity you can derive how large. You cannot derive how large an atom is, but you can derive how far an atom has to fly to hit the next atom. This you can derive from the viscosity, and this is what Einstein did in like 115 years ago, like 117 years ago. So this is not too old. Yeah. So I knew some people who lived before this time. Okay. This takes us now to the third picture, which is the kinetic, which is the one that we are dealing with in this lecture series, which is called the kinetic, and sometimes it's called the mesoscopic. So I'm not a big fan of saying it's mesoscopic because this has a little bit sometimes wrong implications, but this is the way it's usually called. Okay, and this is probably one that you have not heard of. This is the Boltzmann transport equation. Which we will call BTE. So this is a beast on its own, and we should actually also have a complete lecture on the Boltzmann equation, but we have here a lecture on the Lattice Boltzmann equation, so we'll have a simplification of this thing. But now let us have a look what is the Boltzmann equation actually. So the Boltzmann equation has a time derivative of something that is called f, which is a probability density function, plus something that now turned out very ugly. This is supposed to be a vector xi, which is a vector of microscopic velocities, time spatial derivative of f. So this again is an advection operator, and here, okay, comes something that I just right now notice I left out of the Navier-Stokes equation. Yeah, okay, but it's not so important. There is a forcing there's a forcing term, which is a force times a derivative in a vector derivative in the velocity space, in the microscopic velocity space on F. And this is equal to a collision operator. So this altogether is the Boltzmann transport equation. So now what is the difference between the Boltzmann transport equation and the other two, and why is it somehow considered to be in between? So the idea behind this kinetic approach is that molecules, so we still have molecules, this is important, we don't have a continuum, we have molecules. But there's something drastically different, namely these molecules are now undistinguishable. So this is very important. Undistinguished. Do I write it with H? I misspelled it on my... So they cannot be distinguished. Particles. And they are still following Newton's laws, though there's conservation of mass, energy, and momentum, and so on. Okay, so what is the difference? So previously I said there's one molecule entering this room, and then we are observing this one molecule. Now what we say is there is maybe nitrogen and there is oxygen, yeah? And all nitrogen molecules are the same. The only thing that we're caring of is there's nitrogen and not there's this nitrogen. So they are now not counted. So we forget completely about their individuality, yeah? And only have a statistic. And this statistic is expressed by this probability density function F. This is the probability density of, so what does this mean? This is the probability of finding a particle in now, unfortunately, seven-dimensional, so we have 7 dimension here, phase space, as it is called. And this phase space is composed of the location. So location, we write R, yeah, location, this is the odds vector location. What is? XYZ. Yeah, X, Y, Z. So it's X, Y, and Z. So this is the position. So these are 3 of these 7 variables. And then there is the microscopic velocity, which unfortunately we use Greek small Greek letters, so this is a small xi, yeah, and okay, so maybe a little bit, okay, I don't know whether this nomenclature is completely consistent, but we write a small xi vector for all of them, and this is composed of, for the x direction, it is a small xi without vector, yeah. And then, okay, now comes the letters that you never use otherwise. Small epsilon. Yeah, so this is the last 3 letters in the Greek alphabet. I'm very sorry. Yeah, so because you have usually the macroscopic velocities, no, they're not the last. So okay, so very, very far in the back. Yeah. So xi, epsilon, and zeta. Okay. So Anybody has difficulties with remembering what is xi and what is zeta? You know, the thing that you need, the only thing that you have to remember in order to know what is xi and what is zeta is that so zeta is the snake, is the living snake, yeah, and xi is the snake where you make a knot in their neck, yeah. And if you remember this, you will never have difficulties distinguishing xi and zeta. Okay. So these are the three velocity components, and then we still have the time, which is then number 7. So time is t. And this is now the statistics of particles instead of individual particles. Okay, and one warning, this mesoscopic. The mesoscopic in the name does not mean that this is now only usable to cases where you are somewhere in between atoms and, you know, the continuum. Yeah, that's not what it is. So it's not dependent on the size. That does not mean that the theory would be applicable only to a certain size. In principle, they should all be applicable to all sizes, but of course, the what do I write? So, but of course, please.
What does mesoscopic mean?
Meso is in between. Mesoamerica is in between South and North America. Yeah. So, and the idea here is that this is a description that is in between the description of a continuum, where you don't know anything about molecules at all, and between the individualized molecules. Yeah? So you do something in between. Yeah? You still have molecules, but these molecules are now no longer distinguishable. Yeah? So you have just a statistic of the molecules.
And this means that we shouldn't be tricked with the working system.
Okay, so we should not be tricked by thinking that there is a certain size of the system where you do molecular dynamics. Yeah, so if the thing that we want to understand is so and so small, then we have to use molecular dynamics. If it's so and so large, we have to use the Navier-Stokes equation, and then there is a gap in between somewhere where you have to use the Boltzmann equation. Yeah, this is too simple a view of the world, but you will certainly, if you look in any book or something, you will certainly read this somewhere. Okay, let's look at these parts of the of our equation now. So we have the time derivative f of our probability distribution function. This is of course very simple, the change with time. Then we have this plus xi dot f, nabla f. So this is the usual nabla, so the derivative in space. And this guy here is the advection. So in the Navier-Stokes equation, we have an advection, and here we also have an advection. Then we have here a fourth term. This is something that I forgot to write down in the Navier-Stokes equation. So in the Navier-Stokes equation, you could also have a force term, but I left it out, unfortunately. So what does force term mean here? What we mean by these forces here are the long-range forces. Long-range forces is something that doesn't necessarily in the real physics it doesn't really play a big role, or only the gravity probably. So long-range forces are these forces that you assume somewhere, yeah, which are not balanced, yeah, where you say, okay, we are in a gravity field and there's gravity. This gives us a force this from very far away, yeah, and this acting on all of my particles. So these forces I put here, yeah, in order to distinguish them from the short-range forces. So short-range forces are the forces that act between particles which come in contact to each other. So these are the binary forces that we previously spoke about in the atomistic view. So, and this is here in the collision operator. So this thing here does the collision, and this is the short-range forces. So these are the forces that act when things come into contact, meaning they have collision. So there's something very interesting with this advection thing. So first of all, let's look at it. We have here, of course, a particle, and this particle is at time t, it is here, and at time t plus dt, it is there. So it has moved in this direction, and here it is at position r, and up here it is at position r plus dr, yeah? And now it is, of course, moving with its velocity, saying that the velocity xi, this is the change in its position over time. Okay, so this is the microscopic velocity. How does one particle change its position over time? So particles move in the direction of their velocity, of course. So, and remember that h is a function, f is a function of the velocity, the microscopic velocity. So this is very important. We always have to distinguish between microscopic velocity, which is the thing that we have in the Boltzmann equation, and the macroscopic velocity that we have in the Navier-Stokes equation. So, and now there is this very interesting thing. We have an advection operator in the Boltzmann equation, and we have an advection operator in the Navier-Stokes equation. Yeah. So let's write them down again. I leave here a little bit space because I want to write something on top. So the change of the macroscopic velocity in the Navier-Stokes equation. Yeah. So this, now we should write Navier-Stokes equation here, NSE, plus u dot nabla u. So this is the advection of the velocity. The velocity, the macroscopic velocity, is self-advecting. Okay? So it is self-advecting, so we have a multiplication of u and u, with something related to u squared. So this thing here is non-linear. And the non-linearity of this thing is one of the big troubles that we have in solving the Navier-Stokes equation. Now look at this terrible Boltzmann equation, dtf plus xi into the scalar product on nabla f. Okay? Boltzmann transport equation. This thing is linear. So there is no nonlinearity in the advection operator, which is one of the big advantages of the Boltzmann equation, even though the Navier-Stokes equation is only in 4 dimensions, so it is space and time. The Boltzmann equation is in 7 dimensions. Yeah, but therefore we have a linear advection operator. So, but then we have to deal with the collision, which is the thing that now becomes more complicated. And what we will assume is that there's only binary collision. So usually, if there would be collisions of more than 2 particles at the same time, you could decompose them into collisions of 2 particles each. Yeah? So this is why we only look at 2 particle collisions. But this is important that we only, that everything, so the theory that we build is built on binary collisions. So binary collisions means 2 particle meeting. So when two particles collide, so they go either this or this way, yeah. So then they come in, they change their direction and they go out again. So they do this in 3-dimensional space. Okay, no, okay, so no, okay, let me try it first. So we have particles in velocity space. So this is supposed to be now xi and upsilon. So it's now drawn 2-dimensional, obviously, yeah. And there is one particle coming in. This we call xi1, is particle 1 coming in. And another particle at another angle comes xi2. And then they leave. They come in this angle and then they leave at that angle, at a different angle. Say this is now xi1 dash, and this is xi2 after collision. Yeah, so we call this here. So the black one, I hope you can distinguish this. This is pre-call, and the blue one is post-collision state. So, and they will end up on this circle, and the reason why they will end up on this circle is because the collision has to conserve energy, and this is probably better understood when we draw this in a different frame. So now this here is in the so-called laboratory frame. What is the laboratory frame? Can somebody explain what the laboratory frame is? Not you. Frames of reference. Inertial frame, this you learn. So the laboratory frame is a frame where I said okay, we are in the laboratory, I'm sitting on my desk and I define myself as being at rest. Yeah? And everything else is moving relative to me. Yeah? So this is not related to the problem. There's something else, this is a center of mass. Center of mass frame is one that we need quite often. So we can draw the same picture in the center of mass frame of reference. So center of mass is we are now moving with the average velocity of these particles. Yeah? So when we are moving with the average velocity of these particles, there's something very interesting happens. They never come at a strange angle, right? Because they come at a strange angle only because they have a common component in their velocity. So if we put us in the frame of their average velocity, they can only hit head on. Yeah? So if we are in the center of mass, frame of reference, they will always come this way. So Xi1 and Xi2 will always come this way. This is not a very beautiful Xi. And also, because they have to conserve momentum, they have to go out the same way. So they always go out head. So they come in head to head and they go out tail to tail, so to speak. So then this here G is then Xi1 dash and this here is Xi2 dash. So this is what happens. So this is how it looks in the center of mass frame of reference. And what can we say now about these collisions? These collisions have some conservation laws. I should write in black to be consistent. Conservation. What is conserved in these collisions? Everybody gives me something that is conserved, starting from you. What is conserved in the collision? Energy. Okay, energy is conserved. Okay, I probably, because I should probably write this down here to be energy. So, what is conserved? Momentum. Yep. Momentum. Okay, sorry, I left you out.
Yeah, but I want to say mass.
Okay, now, okay, then there is mass I put here. So now you have to, okay.
Angular momentum?
Yeah, angular momentum would also be conserved in principle because there's no, yeah, this is also, it's not on my list, but it is conserved. So, okay, angular momentum is still conserved. What do we still have? Do I have mass? Okay, I have only one more thing on the list. Now I have to. Something very simple, probably too simple. The number of particles is conserved. Yeah, this is 2 coming in, 2 going out. Okay. So I agree, the other ones have been more obvious. Yeah. So these things are all conserved in here. And we look at 2 in particular, namely the momentum. So we can express this in an equation, namely that there's a mass m. Let's say the particles have the same mass, so that we just call them m. Okay, m. We do not distinguish them, though they would have the same mass. So Xi1 plus Xi2 is equal, so this is the incoming pre-collision state, is equal to the mass, the sum of the momenta of the outgoing case, and energy is 1/2 m and the velocity square. So now the velocity square is xc1 times scalar product itself, yeah, plus xc2 scalar product itself would be equal to 1/2 m. So this is something that you can erase. Xc1 after collision times xc1 after collision plus xc2 after collision times itself. So this is the definition of of energy, and this is conserved, so this is something that happens to be that gives us information on what is coming in and what is going out. So now comes the first important invention of Boltzmann in regard to evaluate these things, and this is the so-called molecular chaos. Molecular chaos. So molecular chaos is the proper English word, but even in the English literature, you will still read the real Austrian word that is so-called Stoßzahlansatz. So this is a proper scientific term, Stoßzahlansatz. This is how Boltzmann called it. Molecular chaos is something that sounds too much 20th century. So Stoßzahlansatz is the assumption that Boltzmann made, because he does not distinguish between particles. He also does not distinguish between collisions of particles. So the only thing he is caring for is how many collisions happen. Yeah? And the assumption behind this is that that everything depends only on the number of the collisions and not on anything else. And for this to be true, the particles should not know anything about each other beforehand, which mathematically expressed is colliding particles are uncorrelated. So what does it mean is uncorrelated? Uncorrelated means that if you know something, so I give you one particle, and I tell you everything about this one particle, and you know everything about this one particle, and then you still know nothing about every other particle. This means uncorrelated. Yeah? And the thing, okay, so when particles collide, they are in the same position. Okay, so this is probably something that we could know, yeah, but we do not know anything about their velocity. So this means that the velocity of particle 1 is not influenced by the velocity of particle . By the way, this is completely an assumption, because this is not clear and is most likely not even true, right? But it works very well. Yeah. Okay, so this was his assumption, and what we then do in order to simplify things is we use a parametrization of this collision. with the direction. And this direction is expressed by a vector which we call small sigma. So it's supposed to be a small sigma. And the sigma gives us just a direction, which means it has length 1. So this sigma just tells us, so how do I rotate? If I very, very briefly, I don't like to do this, but I just very briefly go back to this picture of the center of mass collision. Yeah, the sigma tells us by what vector do we rotate these outgoing particles, yeah, in order to get the new velocity. So, okay, let's go back here. So the particle after collision, which is written with this dash here, so this has nothing to do with the derivative. Particle 1 can be expressed, first of all, by the center of mass of the velocity. So this is the center of mass velocity, obviously, plus, now comes the magnitude of the difference between these velocities divided by 2, and this multiplied with a direction vector. It's the outgoing direction vector. So this is particle 1. And in the center of mass system, so the center of mass we put in front, right? This is the center of mass. And in the center of mass system, the other particle has to go exactly the other way. So we already know that then that Xi2 after collision is again the center of mass. Now minus, because going exactly the other way, Xi1, so this is the incoming, so the difference between the incoming velocities times sigma.
What is sigma?
Sigma is the direction. It's a vector that just gives the direction. It's a parameter, yeah. So could be anything. So we know particles go in, but we don't know where they are going. Yeah. So they could be anything. The only thing that it has to have magnitude 1. Okay, and with this, Boltzmann derived the so-called collision integral. Collision integral, which is a long thing to write, so I have to start very much here in one corner. So the collision integral can also be expressed as a time derivative of the distribution Xi for only the collision, no advection. Yeah, so this is time derivative of the of f due to collision, and this is now a double integral over capital sigma. Capital sigma, sigma is the direction. Yeah, so the small sigma is the direction. So this means all directions. An integral over all possible directions, because it could come out in any direction. And an integral over all speeds. So over all speeds of the particle too. So this, I write a capital sigma over all directions, because sigma is the small sigma is the direction. Yeah, velocity is small xi, so I write a large xi, meaning all the velocities, yeah, the entire space. So this is a large xi, if you're not completely familiar with the Greek alphabet. And now we have something that's called a collision kernel, that is a function b, which we currently do not specify specifically. That is, but this function b is dependent only on the difference between the particle velocities, not on the absolute velocity. And the direction. And now this has to be multiplied with the probabilities of particles actually meeting each other. Yeah? F is the probability density function of particles being in a certain space. So the probability that two particles meeting each other means they have to, this would be the product of these two distribution functions. So the probability of one particle being there and the probability of the other particle being there, the two being independent of each other by definition through the Boltzmann-Stoßzahl-Ansatz, then the probability of the both being together in the same space has to be their product. Yeah? And this would be now F of, and I write the outgoing guy first. So particles outgoing, going out, is F1 outgoing times F2 outgoing. I write these first because they emerge through collision, so they are positive. This is the gain term. Yeah, so there are new particles. Yeah, this is the particles that are so the probability, so to speak, they are generated. Yeah, they come into the system. This is a gain term. On the other side, the particles that were going in, so the state that was going in is destroyed. Yeah, so they are going out of the system, and therefore I have to write them with a minus. So then there's F xi1. So that was ingoing times is meeting another guy with this other velocity. And this is the loss. So this is the term that is lost, and all of this has to be integrated over the velocity space of the particle 2 and all the directions. So, and now I have obviously forgot to write here in the beginning, yeah, so this is the velocity xi1, yeah? The collision acting on velocity xi1. So, now the important thing about this, what I've already said, I have to write down, the collision kernel, as we call it, B is a function of the relative velocity and the direction only. So not a function of the absolute velocities. Oops, writing is sigma. And we have to distinguish between this gain thing, these are the particles, as we say, scattered into this particular velocity, and the loss is the particles scattered out of a particular velocity state. So, and these things have conservation laws, of course. Now we come back to our conservation. So B has to fulfill some conservation laws. And okay, so this will be the collision integral has to fulfill all the things that we have stated before. Namely mass, momentum, and energy. So if there are, so the thing is, if there are two particles and they are point masses, they also conserve automatically angular momentum in that case. Yeah. So this is why we usually do not mention this explicitly. So they do this by more or less by their form. So this means, so how do we express this conservation laws in the collision operator? We do this by recognizing that if we integrate everything now over velocity 1, over the entire velocity space 1. Now remember, the collision integral is an integral over velocity space 2 of the other particle. Now we integrate over particle 1, and in this particle 1, in this integral, we put the collision operator where we have already integrated over particle 2. Now we integrate also over particle 1, and we multiply this by this phi and do the integration on the particle velocity 1 with phi being a kernel function that comes out of these, that for example could look like this, or no, it would look like this. So because I have three conservation laws, yeah, and these are expressed with this integral. So if I integrate everything, if I integrate the entire collision operator with phi equal to 1, what I would have is the mass of the particles. And the mass of the particles does not change in the collision, therefore the integral must be 0, right? So this, because this here is mass. And the next gives me momentum. So if I multiply the collision operator by the first microscopic velocity, integrate everything, I get the momentum change of the collision operator. It has no momentum change, so it has to be 0. If I integrate with velocity square, I have the energy, it does not change energy, yeah? So it must be 0. So this is how I express so this is how I express the conservation laws in this way in the collision operator. And by the way, something is very important, these things, what we just introduced, so an integral of a distribution say, call this f. Now it could be any distribution, but now it's the one that we are using here, the particle distribution. An integral of distribution f with a kernel phi is called a moment. So for one strange reason, here in civil engineering, people often believe moment. There's only one moment, which is the bending moment. Yeah. So if you say moment, they always think about bending moment. A moment is this is a moment because it's an integral with a function over some space. The bending moment is a moment, but never say just moment, because what you learn here is we'll have zillions of moments. Yeah. So everything we are dealing is with the rest in the, here we are dealing with moments. What is the question?
There is the same. I mean, the kernel depending moment is simply x.
Yeah. So is a first, okay, so the bending moment x means it's a moment in space. Here is a moment in velocity. Yeah? So you can have moments in different, moments in space, moments in time, whatever, but here we have moments in time. Okay. But here we have moments in velocity space. So, and they are, okay, yeah, maybe this I have to write first. So the collision integral has 5 conserved moments. The reason why it's 5 is because the velocity, each velocity component is a moment by itself. Yeah, it's conserved by itself. Yeah, so the velocity moment has 3 components. So there's 3 of them together with mass, together with energy. They are together 5, and they are all conserved. And these conserved moments, they have a very interesting relationship to the primitive variables in the of the Navier-Stokes equation in continuum theory. So because these guys are moments. Okay, they are, to be a little bit more specific than I have on my sheet here, they are mainly, okay, so they are moments. Okay, I don't write this because it's not consistent. They are moments. The one little difference is that most of them are intensive moments. Yeah, so we have one extensive moment. This is why I don't write this. An extensive moment. What is an extensive variable? So if I integrate f just over c with no kernel, or with kernel being 1, and we call this the 0 moment. You know, when the kernel is 1, we call it the 0 moment. Well, because it's the velocity to order 0. Yeah.
Because the order specifies
the exponent. Yeah. So we see this at velocity. Velocity u. So we multiply this. Now our kernel is C1, and there's a little difference here, namely that I divide through the density, through rho, which makes this an intensive quantity. Yeah?
What's an intensive quantity?
An intensive quantity is one, or can you explain, because you didn't get the, can you explain what an intensive quantity is?
Yeah, that doesn't depend on the amount of.
Yeah, so if you add 2 intensive quantities together, you don't get the sum of the other. So the intensity, the density is an extensive quantity because you put more things into it. You get you get a larger. You make the system larger. You get more mass. Okay. Okay, mass. Yeah. You get more mass, and the other one is now in so velocity is the intensive quantity that corresponds to momentum, and what is the intensive quantity that corresponds to energy? Some ideas? So actually what we have here is we have to subtract the macroscopic velocity, and we have to divide through rho times d, and what will this give now? So this corresponds to the energy, but we have taken out the center of mass velocity and we've divided through the mass, and d is the number of dimensions.
And why is the velocity subtracted? Why is it not?
Then it doesn't make, so then we have the total, okay, that would be the total energy if we do not divide it by the mass. Yeah? But we do not want to have the total energy, but we want to have the energy distinguished, the energy, actually the thing that gives us the temperature. Yeah? So if we subtract the, so because u, macroscopic velocity, that would be the kinetic energy of, say, the air, or that we are looking at, the kinetic energy, and the rest, if we subtract this, then it will be the thermal energy, and the thermal energy, of course, gives us the temperature if we take it intensively. So I'm getting, let me see, I hope that I can deal with. Okay, we have something like 17 minutes, and we have the most interesting thing in the world still to learn today. And this is the so-called H-Theorem that Boltzmann proved, and which is one of these very important things here in the world. So it is not known to science because we have no voice recordings of Boltzmann how to read this letter. So in English literature, most of them think this is an H, but an H looks exactly like a Greek ether, and it is believed that what Boltzmann meant, because he was talking about something related to energy, it should not be an H, it should be an ether. So this is why we believe is an H-Theorem, but you will also hear people say this is an H-Theorem, okay? And now the idea behind this is to look where the universe, or where particles go to, and actually where the entire universe goes to. So, and I now write this sentence: when gain is equal to loss, and even though I'm German, I purposely say when and not if. Yeah? So when gain equals to loss, collision, because eventually this will happen, when gain equals to loss, collision does no longer change the distribution, and then the distribution is said to be in equilibrium. Is said to have reached equilibrium. Now, one of the things that Boltzmann wanted to do is to derive how this equilibrium looks like. This is on the way there, he discovered something that's even more interesting. So what the equilibrium is, we learn only next week. Now we look at what he discovered on the way, deriving it. So say I put here an equation 1.1, and this is our collision operator. And this we have decided. So I write the integral without the bounds, yeah, because otherwise I have to write a lot. So we have f1 dash now being in equilibrium times f2 dash also in equilibrium minus f1 equilibrium times f2 equilibrium. So I've not written the arguments of B, so there's a multiplication in this here, yeah? Yeah?
In this eta theorem, what is that distribution signify?
The distribution, this is the distribution we've previously used, the particle distribution. Yeah, let me finish this equation, then so we're integrating over xc2 and so if they are in equilibrium, then there will be no further change, so this means that this here would be equal to 0. Let me briefly, so this f, what I call f1, maybe that's your question, yeah, is a shorthand, because now I have to write a lot of these things, no? is fc1, and if I write f1 dash, this is f1 dash. So, and the equilibrium that I've written up here, this is, okay, maybe mathematically not completely consistent. I just want to imply that now this is the stage. So when they are in equilibrium, yeah, then by definition, this is how we defined it, then nothing changed anymore, and then the collision integral becomes 0, right? Did I somehow also answer your question?
Yeah, bit clear.
Okay. Okay, now Boltzmann, 10 minutes. Boltzmann defined a strange function that will only become clear after some calculations, a function null. So ether of t to help identifying the equilibrium and the thing that he defines H, now I said H myself, ether of t, so is now the integral over f1 times the logarithm of f1, and all of this integrated over xc1 and the entire space. When I say the entire space, I mean the universe. Okay? So we take everything, all velocities, all space, each molecule in the universe, yeah, is included in this. Why is there a logarithm? So this is a big mysterious. So he defined this, and we'll later see what this leads to. Yeah. So he defined this function, yeah, mysteriously, and looked at what happens with this function. Okay, we'll see. Yeah, genau. I have to write integral over all micro velocities and all coordinates. So remember, this is the entire universe, yeah? Otherwise it's not correct. Now, coming to equation 1.2. Now what he did is he did the derivative of h with time, and he put this derivative into the integral, which is now on f of xi1. Now, okay, I notice I've written it just in a different way. I hope you forgive me. Okay, now I write it in a shorthand so that it's consistent. F1, yeah, log F1. So, but remember there is a xi inside, yeah? The xi is inside of this. So, this integrated over xi1 and over the entire universe. So now we can do the, what is it called, the chain rule on this integral, sorry, not the integral, but on the derivative, which means we first take out d dt f1, and this then, so we've put this on the first one, so this goes into the logarithm of f1, and if we take the other part, then the derivative of f, yeah, of f1 would be 1 over f1, yeah, times the f1, which we do not take the derivative of, gives us an f1 divided by f1. Yeah, roughly clear? Okay, so d xi1 dr. And now the important thing is that this guy here is our collision operator. Now we can put the collision operator in this in order to show the H-Therem. Okay, I'm going to finish this. It's, even though I only have 5 minutes left, but so in order to show that this derivative is smaller or equal than 0, and the equilibrium would be the case the equilibrium we have reached if there is no change anymore, and this is when the time derivative is equal to 0. And now the question, of course, is why should this be the case? And for this, we have to put the collision operator into 1.2. So if we do this, we get to 1.3. d Isa by dt is equal, now comes the collision operator times f1 dash f2 dash minus f1 f2, and this goes into 1 plus log f1, and now we have to integrate over a lot of guys, namely xi1, xi2. So xi2 comes from the collision operator, dr, and d sigma, so d sigma also comes from the collision operator. Now we do not distinguish between particles, which means that f1 and f2 are interchangeable, and the integral goes over both of them. Meaning that if this is true for equation 1, for f1, then it will also be true for f2, which means we can write the equation 1.4, which looks exactly the same, with one small difference. So we have again one f1 dash f2 dash minus f1 f2, and here 1 plus. Now there's the only difference is that now we have the logarithm of f2, and here we have the entire stuff again. Now what we can do is we can simply sum these two things together, 1.3 plus 1.4, and you see, because there's the only difference here, it's giving us the equation 1.4. We sum them together, so on the left-hand side we have twice dH by dt is equal to the integral, so most of this guy is the same. So just to rewrite it again, and here we have just 2 plus the logarithm. So if we sum up two logarithms, we get the product of the two guys. So it's f1 times f2. And again, the integral over the entire space. B is multiplied, yes. As I said in the beginning, it's always multiplied. Okay, now there is, okay, I have these 3 minutes left. Now there is another thing, which is very important, yeah? The collision is symmetric, yeah? So it can go in like this and go out like this, and it can also happen exactly the other way around. So it can go in like this and go out like this. So, and I mean, this is the most amazing thing, because you have to keep this in mind. We now assume that the collision is symmetric in time. So it happens forward the same way as backward. And from this will arise that it only goes in one direction. Yeah? The assumption is forward and backward is the same. Yeah? Collision is symmetric. Can go forward and backward. Which means we can exchange F1, F2 dash after collision with F1, F2 before collision. So we get another equation, 1.6, which is the same just with the guys exchanged. So again, twice. The left-hand side is the integral b, okay, b multiplied by, now I exchange, yeah, these distributions. Now they come before collision minus the one with the dash here times 2, and now comes log the f1 dash, f2 dash, and all of this is still integrated over the entire velocity space in both directions and over the entire universe and over all directions. Now we are almost done. We are also almost done in time. The last thing that we do now, after we exchanged also the direction of the particles, we sum equation 1.5, which is the forward direction, together with the backward direction, 1.6, which gives us 4 times this. 4 times d h dt, the integral b. Now I put them together in a common direction, and I take this common direction from 1.5. Yeah, f1, f2. So because they have different sign, the 2 that comes in both of these equations, this will be eliminated due to this inverse sign, and the other one will go log f1, f2. This is coming from 1.5 minus log f1 after collision times f2 after collision, and the entire thing dxi1 dxi2 xi2 d sigma and d rho, and this thing here is smaller than 0. Okay, I'm doing 2 minutes overtime, but I have to explain this. The proof is done. This is the proof. You only have to see it. Yeah, this thing here has to be smaller than 0 because, so why? The logarithm is monotonic. The logarithm is monotonic. So this means that if f1, f2 would be larger than f1 dash, f2 dash, yeah, then if this is the case, or smaller, if this is the case, and the guys here, so this bracket here would be negative, right? But in the same way, the logarithm would then also behave the same way, right? And here on the other side we have the logarithms, but the other way around. So this is why we put the logarithm into it. So meaning that if the first bracket is negative, the second bracket will be positive, and if the first bracket is positive, the second bracket will be negative, and so this is always negative. So this is always either smaller than 0 or it is 0. And this means, because this is a time derivative, the time derivative is always negative. So this means that ether provides a direction in which things happen. So everything in the universe changes such that ether becomes smaller. And the very interesting thing is that the assumption that everything here is based on is that the collision is symmetric in time, that it can go one way exactly the same as the other way. So from the assumption of reversibility, okay, let me Bill collisions arises the irreversibility of the system. So if parts are reversible, then the system is irreversible. So this was the intuitivity. Okay, I'm 5 minutes, I think, over time. I have 2 more sentences that I just write. Okay, I'll write them down. So the system goes closer and closer, so it's approaching to equilibrium. Equilibrium is the state where entropy does not change anymore. So if this is 0, and this here is, eta is the scaled negative, so he has unfortunately got the wrong sign to it, the scaled negative entropy. Okay, sorry for doing overtime today. Yeah, any further questions? So in this, you have to do a homework for this course, and I believe I sent you an email that you have to choose one of these 10 assignments, and have to write a little bit of code in order to do this. Here we of course start first of all with theory in order to understand how things actually work. Okay, but get your assignment, so please form some groups, so groups up to 3 persons. If you really, really like, you can also do it alone, but I do not suggest this. Okay, then see you next week.